Hi there. So I am going to talk about lesson 14, which discusses least squares lines or regression lines. Prior to talking about this, I just want to give you a little bit of the motivation as to why we're even going there. So in life, as you know, nothing is perfect. Um, and in particular here, we tend to try to model real life situations in mathematics. And one of the ways we do that is by finding functions that best approximate various real life phenomena. Okay, so we've been talking about linear models in terms of cost and revenue and profit and that sort of thing. But more generally speaking, while things can be approximated using a linear model, rarely does data perfectly fit a linear model. Okay, so we might be in a situation, for example, if we were going to plot a bunch of data where suppose this is our data. Okay, now this doesn't fit a line perfectly, but I claim it sure does a good job of approximating a line. The question is, what line would best fit this data? Okay, so, we could say, well, there's this line right here. It might fit some of the data perfectly, but in general, what it does is it best approximates the data. Okay, similarly, we might plot a bunch of data values that look like this. And again, we can approximate this using a line. Again, it doesn't necessarily fit all the data that perfectly, but it certainly gives us an approximation. And why would we want to do this? Well, very often we find these linear models so that we can make future predictions. Okay. Now, it's not just linear models that can happen. I mean, for example, a function that we study in other classes in mathematics are what we call exponential functions. I wouldn't try to draw a line to model this data, but we could certainly draw an exponential function to do such. We're not going there in this class. Now, the issue is, what if you have a bunch of data like that? Okay, mathematically speaking, we could find a line that, let's just add a few more, that best fits this data. Okay, just to approximate it, maybe right here. Would we want to use this line to make any future predictions? I claim no. You're not going to have much accuracy. So there's a couple different issues going on. Okay, given the fact that life isn't perfect, how do we find a line that best fits the data? Number one. And number two, how do we know if we didn't plot the data, if that line is at all a good fit? Okay, so those are a couple of things we're going to be addressing in this particular section. Now, one comment that I want to make is you are not responsible for finding the equation of the line that best fits the data. Okay, technology does that. You're going to delve a lot more into that if anyone is going on and taking, for example, a statistics course. Okay, our calculators do provide that for us amongst a lot of other technology. But what's really important to me is for all of you to realize that everything we've done so far is textbook perfect in the sense that everything fits a line exactly. And I want you to see that that just is not what happens in practice, number one. And number two, given the least squares line, I want you to be able to interpret what does the slope mean in the context of this line, and what does the y-intercept mean in the context of this line. And we've done that already, for example, with our cost functions. Okay, so just briefly, what I want to say is two things that you're going to have to interpret are our y-intercept. Remember, that's our b value. And more specifically, That's the value of y when x is equal to 0. Okay. Sometimes we call that our initial value. So what I'm going to do is kind of give you like a broad script for how we're going to do these interpretations. So for example, to interpret our y-intercept, essentially what we'll say is when whatever x represents, but we like to put that in the context of the question, is 0, then whatever the y value, again, represents in the context of the question is b. Okay, b from the y equals mx plus b. Okay. This might seem funky right now, but what I'm giving to you here is a template. The other thing you're going to be asked to interpret is the slope. Okay. My hint for interpreting the slope is always to use units. It's the change in your y or your function value over the change in your x value or your inputs. And a template that you can use for right now to get us started with doing the interpretations is for each additional increase in whatever our inputs are, whatever your output is, either increases or decreases by whatever your slope is essentially. Okay, so think about it this way. When we were talking about the slope of the line, what we were saying is for every horizontal move we make, what is the vertical shift that we make? Okay, so that's why we say for each increase in our x value, we want to talk about what happens to our y values. We know they increase if our slope is positive, and they decrease if our slope is negative. Okay, again, this might seem funky right now. Just keep this template by your side and you'll see how we use it as we go through a couple of examples. Okay, I'm just going to do probably 2 examples here and then just talk about how to tell whether or not the line is a good fit. Okay, so this first example that I'm going to do is a little bit outdated, but it's amusing to think about. And what I'm going to be talking about is the percentage of US households with internet at home. And I'm going to let X represent the number of years since the year 2000. And I'm going to let Y represent the percentage of homes. Okay, I'm going to tell you that suppose we collected a bunch of data, okay? And we found that the line that best approximates this data is as follows. And again, in this section, I will always give you the line. I promise, okay? Technology can do this. We don't need to in this particular class, okay? So the first thing I want us to do is interpret our y-intercept. And in order to do that, what we need to ask ourselves is, what does it mean for x to be equal to 0? Okay, because by definition, the y-intercept is the value of y when x is equal to 0. Okay, Well, what we're saying is if X is the number of years since 2000, we're saying 0 years after 2000, which I would interpret as in the year 2000. Okay. In other words, the year 2000 is our starting value here. So what we could say is as follows. In the year 2000, again, I'm using this template we had. When X is 0, we've interpreted that as the year 2000. Well, then what happens? In the year 2000, well, our y-intercept is 43.7. We can say that 43.7% of US households had internet. Okay, again, when you interpret the y-intercept, you're asking what happens when X is equal to 0. So first we determine what it means for X to be 0. And then we say, well, this is our y-intercept. And that stands for the percentage of homes that have internet. All right. Why don't from here, we then interpret our slope? Same line. So let's interpret our slope now. Okay, again, in my hint to you, when we talked about how to do these interpretations, you want to talk about units. So we need to determine our units. Well, the units for our y values are percentage, and the units for our x value is years. Then using the template that we had, I'm going to have that right above here. For each additional year after 2000, so for each additional increase in our input, well, we could say the percentage of US households with internet notice that's your output. Well, notice in this example, my slope is positive. So what we're going to say is the percentage increases by whatever our slope is, 2.68%. All right. I know this is kind of funky, but you know, so often in math, historically, people just do a bunch of computations, but the computations are really meaningless unless you can interpret them and put them in the context of what you're looking at. And because all of you are taking this class, presumably for your major, the hope is that you're going to be using these ideas as they pertain to whatever it is you're studying. All right, another example. I'm going to now let X represent the number of police on duty. And I'm going to let Y represent the number of muggings in a city park. And suppose I tell you that the line that best approximates this data is as follows: negative 0.464x plus 9.68. Okay, so what we're claiming is that there's a legit relationship between the number of police on duty and the number of muggings that take place in the state park. Now, one would hope that the number of, as we increase the number of police on duty, the number of muggings decrease, but I claim we'll see that because we have a negative slope. All right, so first let's go through and interpret our y-intercept. We see that our y-intercept is 9.68. Okay, it's important first to be able to identify what that is. So the first thing that we're going to do is ask ourselves, what does it mean for X to be 0? Well, it says, well, when X is 0, when there are no police on duty, well, this gives us our Y value, which is the number of muggings. There are 9.68 muggings. Okay, again, just as we did with the previous example, we first say, what does it mean for X to be 0? Put it in the context of the question, and then give our Y-intercept in the context. All right, so then the next thing that we're going to do from here is interpret the slope. Again, I always start out by dealing with units. And notice that the units for our Y value are muggings. So number of muggings, and our X value is the number of police on duty. Okay. And again, using that template that we have. Okay, I'm going to grab it again just so that we have that here. Using this template, for each additional increase in our inputs. In other words, for each additional police person on duty, okay, right, for each additional inputs, in this case, it's the number of police on duty. Well, what happens? Our output, which is the number of muggings, right? Well, does it increase or decrease? Notice here our slope is negative, and it decreases by whatever our slope is, and in this case, 0.464. Now, I know these numbers seem rather nonsensical, but remember, these are the lines that best estimate the data, so they're an approximation. All right, well, because we have an equation of a line, we might as well use it for one more thing. What if I asked you, given this line, how many police would be needed for there to be no muggings? Well, remember, we have two unknowns. We have X representing the number of police, and we have Y representing the number of muggings. We need to be given one so we can find the other. And notice here, we're looking for the number of police. In other words, we're looking for our X value. So we better be given our Y value. And in this case, we want our Y value to be 0. So what we're going to solve is this equation right here. Well, what would be my first step? We could move the 9.68 over by subtracting it from both sides. So we have negative 9.68 is negative 0.464x. And now we want just x. So the way we undo multiplication is division. We'll divide both sides by 0.464. And if you do that, you're going to get about 20.86. Okay. So again, we need to interpret this in the context of a word problem. 20 police are not enough. Okay. So in this case, you would say 21 police people. All right, so the worksheet that you're going to have the opportunity to work on will provide a lot more practice for this. Now, another point that I would like to make is as follows. So far, I've given you the least squares line, and I haven't told you whether it's a good fit or it's not a good fit. And again, this is something you're going to explore a lot more deeply when and if you're in a stats class. But essentially, if your data looks like this, I would use that line. I'd say that's a pretty decent line. Use it. Okay, we'll at least get some decent predictions. On the other hand, if this is our data, that would probably look like the line that would best fit the data. I would not bother using that. Nope. Okay, it's just not a good fit. So what we're asking at this point is, how can we tell if the line is a good fit? Now, this is extra. Really, what I'm going to ask you to do on a test in this section is be able to interpret your slope, interpret your y-intercept, and maybe do a computation or two, okay? Again, you're going to go a lot more deeply into this in a stats course. But the way we can tell, and fortunately, when your calculator computes the least squares line, it also gives you this information. It's called the correlation coefficient, and that's symbolized by an R, okay? And the sign of the R matches the sign of the slope. So if your slope is positive, so is R. And in particular, R is between 0 and 1. On the other hand, if your slope is negative, so is R. And in that case, R is between 0 and -1. So my point is this: the sign of your slope does not tell you how good of a fit it is. The sign, the sign of your correlation coefficient does not tell you how good of a fit it is. The sign of the correlation coefficient just follows the sign of your slope. Okay? Well, here is our rule of thumb. The rule of thumb is it's a good fit if R is between either 0.8 and +1, that's if you have a positive slope, or -0.8 and -1. It's a moderate fit. In other words, you can use the line, but use some caution. If R is between either 0.5 and 0.8, or in the case that we have a negative slope, -0.5 and -0.8. And finally, it's a bad fit, AKA don't use it, if R is between either 0 and 0.5 for a positive slope, or 0 and -0.5 for a negative slope. Essentially, what we're saying is the closer our correlation coefficient is to 1 or -1, the better of a fit it is. If you actually come up with a line that has a correlation coefficient either equal to 1 or -1, that means that the line is a perfect fit for the data. Okay, and again, this honestly only happens when you're in a textbook situation. And I suppose perhaps some very, very rare circumstances otherwise. All right, so what I want to comment on is as follows. Let me share my screen. Just going to show you this lesson 15 online homework so that you can get an idea about what you're going to be doing. Notice there's only 5 questions, okay? So what I want to comment to you about with this is as follows, okay? Number 1, here they gave you a bunch of data, okay? And they tell you what X represents, and they tell you what Y represents. You do not need to find the equation of the least squares line. They give it to you, okay? It's right here. And so what they want you to do is answer the questions based on this line, okay? So for example, in part A, they want to know the number of murders per 100,000 residents, okay? In other words, we want to find our Y value, and notice they give us the X value already in the appropriate units. So literally all you would do here is plug in 6.7 in for X and solve for Y, and they say round to 3 decimal places. And notice they also want you to do the same computation when X is equal to 3.2, okay? So all you're doing is playing with the given line. Question number 2 is very similar. Now we're talking about the number of years since 1995 and the corresponding retail sales in billions of dollars. And they even graphed the line for us, okay? And gave us the equation. So the first thing is this line a good fit? You can look at it and answer that. And then what they want you to do is estimate the retail sales in the year 2017. Okay. Notice here that we have our input, which is T, to be the number of years since 1995. So if we're talking about the year 2017, the first step we have to figure out is what would we plug in for T? Well, how many years after 1995 is the year 2017? I claim that it is 22 years later. So in this case, I would plug in 22. And then I would get my answer there. Okay. Now, for this second part, we want to use this model to predict the year when this will be 238 billion. So now what you're going to do, notice this is already in billions, so you don't have to add on all the zeros, is you're going to put 238 here, and you're going to solve for T. But notice you're not done at that point, because what you found with T is the number of years since 1995. So you're going to want to take that value of T and add on 1995. All right, so question 3 gives you what it looks like in the calculator if you were going to be computing it, okay? So typically in our calculator, what this does is it says Y equals AX plus B, and they give you the value of A and they give you the value of B. There's nothing you need to solve here. The only thing that you're going to want to do is say, oh, well, given the values they have here, we have Y equals negative 0.98X plus 22.826. Okay. So here they just show you how it looks in your calculator. Now that you have this line, what you need to do is then plug in and answer the corresponding question, okay? In this case, they want you to predict the number of sit-ups, which is Y. In this case, you would just plug in x equals 13. All right. So I then will just show you in this next example, they have some scatter plots. Okay. In other words, they plotted the data. And what they want you to do is match each of these 4 data scatter plots with the corresponding correlation coefficient. Okay. So notice A and D are both positive. So you're going to want to link those with whichever scatter plot shows a positive growth. And the 0.3 is going to be for the one that's not as good. In fact, this has a positive slope, right? Notice as our x values are getting larger in general, so are our function values. So I would say this one is A. This is also a positive one, but notice this is much more solid of a line. So that would be D. Notice that the other 2 are decreasing lines, and this one is a heck of a lot better than this one. So since I have 2 negative correlation coefficients, and since this one is the better one, we need to find the number closer to -1, and this would be B. And then finally, the last one would be C. Okay. And last but not least, nothing to compute here. What they want you to do is just plot the points and then find a line that best fits the data. So for example, if we wanted to plot the points, the ordered pair 11, 5, well, my x-axis is my first quiz, my y-axis is my second quiz. So here's 11 and here's 5. And then I need to plot 21, 18. So here's where our first quiz is 21 and our second quiz is 18. And we would plot that point, excuse me. And they want you to go through and do that for all 8 of the points. And I haven't done that for this, but if I was just going to be finding the line that best fits this data, I would just draw this silly line, right? But you want to somehow approximate it. All right. I'm happy next Monday to answer any and all questions you might have on this. Thank you.